Now that we've seen what the chain rule for partial derivatives is, and we know how to make a dependency diagram, we're going to put that into action with a few worked examples. Okay, for our first example, we're going to take a look at z, which is a function of x and y, and then we can see that x and y are both functions of t. So we want to find dz dt. So we're going to start with a diagram. We have t, which is a variable for both x and y, which are the two variables that build z. So if we travel along this, up here we're going to have dx dt. Since x is just a function of one variable, we don't need a partial derivative there. Same for dy dt over here. But then because z is a function of both x and y, the lower half of the diagram, we're going to use partial derivatives. So this will be dz, the partial of z with respect to x, and then the partial of the partial of z with respect to y. So if we use our rule, which is multiply along the paths and then add the paths together, we see that dz dt is going to be the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. So now we just need to figure out what each of those pieces is. So if we look at z equals x cubed plus 2xy, we'll find the partial of z with respect to x first. So we're going to treat y as if it's constant. So we'll get 3x squared and then plus 2y. And the partial of z with respect to y, now we're holding x constant. So the first term goes to 0, and then we just get 2x. And then we'll look at dx dt. Dx dt is 2t, and dy dt is the derivative of natural log. We're going to get 1 over t plus 2. All right, so now we can build this with all of the pieces. We get that dz dt is going to be dz dx, or the partial of z with respect to x, so 3x squared plus 2y times 2t plus the partial of z with respect to y, so 2x times dy dt, 1 over t plus 2. But we're looking for a function that is with respect to t, so we're going to now swap out all of our x's and y's. So x was equal to t squared minus 1, so we get 3 times t squared minus 1 all squared, plus 2 times y, which is natural log of t plus 2, all times 2t, plus, now we replace the x again, 2 times t squared minus 1, all over t plus 2. And there might be some more simplification there, but we're going to leave it in that form for now. Okay, in this next example, we have f as a function of x and y, but then we also have that x and y are both functions of r and theta. So we need to find the partial of f with respect to r. So if we draw our diagram, we're looking for the partial of f with respect to r. So we start with r at the top and f down at the bottom. And x is a function of r and y is a function of r. Notice we could add a theta here if we wanted to, and we could look at that diagram as well, which would enable us to find the partial of f with respect to theta. But that's not what we want to do here, so we're just going to stick to our diagram for r. Okay, so let's fill in the pieces that we need. We need the partial of the partial of x with respect to r, and then the partial of f with respect to x, and then we need the partial of y with respect to r, and the partial of f with respect to y. So notice as you move down the diagram that the lower term of the path that you're on is in the numerator, and the upper term on the path that you're on falls into your denominator. All right, so we see that the partial of f with respect to r, multiplying along paths, we're going to get the partial of f with respect to x times the partial of x with respect to r, plus the partial of f with respect to y times the partial of y with respect to r. All right, so now let's look at each of those pieces. So f of xy is e to the xy, which means that the partial of that with respect to x is going to be y e to the xy, and the partial of f with respect to y is going to be x e to the xy. Then let's look at the partial of the partial of x with respect to r. So x is r cosine theta and y is r sine theta, so that the partial of x with respect to r, so now we're holding theta constant, so we just get cosine of theta, and the partial of y with respect to r is going to be sine of theta. All right, so now we're going to put all of our pieces back together. So the partial of f with respect to r is going to be the partial with respect to x, so that's y e to the xy, times the partial with respect to r, so we get times cosine of theta, plus x e to the xy times sine of theta. And we can simplify that a little bit by pulling out this e to the xy, and then we're going to get times y cosine theta plus x sine theta. And now we can replace, we want our answer in terms of r and theta, not in terms of x and y. So we'll replace all of our x's and y's. So we get we're going to get r cosine theta, r sine theta times r sine theta cosine theta, replacing y there, and then r cosine theta sine theta, replacing x. And we can tidy that up a little bit. So we get e to the r squared cosine theta sine theta. And then notice here these terms, because of the commutative property, they're the same. So we have 2r sine theta cosine theta inside of our parentheses. Okay, this one's not too dissimilar to the last one. We have z as a function of x and y, and x and y are functions of u and v, and we want the partial derivative of z with respect to u. So we're going to remember when we look at this that the bottom letter goes at the top of our diagram, the top letter goes at the bottom of the diagram, and then we're going to put all the intermediaries in there. So we have an x and a y here. And so we see that we need to know what is dx, or the partial of x with respect to u, and the partial of y with respect to u. And those are both partials because x and y have two variables, the u and v. And then we need the partial of z with respect to x. So again, the lower letter goes on the numerator and the upper letter goes in the denominator when you're figuring out which way to write these. Okay, so let's figure out our pieces. So we have that x is u minus v, which means that the partial of x with respect to u is just 1. And we have that y is u squared plus v, which means the partial of y with respect to u is 2u. And then since z is x squared y plus y cubed, the partial of z with respect to x, we're going to treat y like it's a constant, so we're going to get 2xy for that. And the partial of z with respect to y, now x is a constant, so we're going to get x squared plus 3y squared. Okay, so now we can put it all together. Using our formula, remember we're going to multiply along the paths and then add the paths together. So we get dx, the partial of x with respect to u times the partial of z with respect to x plus the partial of y with respect to u times the partial of z with respect to y. And plugging everything in, we get 1 times 2xy plus 2u times x squared plus 3y squared. And because we're looking for du here, we're going to switch this back to u's and v's instead of x's and y's. And so we get 2 times u minus v times u squared plus v for the 2xy term, and then 2u times u minus v squared plus 3 times u squared plus v squared. And we could go ahead and expand all those terms out if we wanted to, but I'm just going to stop there. Okay, so this next one is not too tricky. We have z as a function of x and y, and both x and y as functions of s. So we're looking for dz ds. So we know our diagram, we're going to have an s on the top, z on the bottom, and we're passing through x and y on those. So we're going to be looking for dx ds. X only has one variable, so we don't need a partial there, and dy ds for the same reason. And then the partial of z with respect to x and the partial of z with respect to y. So dz ds is going to be multiplying. We'll get dx ds times the partial of z with respect to x plus dy ds times the partial of z with respect to y. So let's figure out all the pieces we need. Since x is equal to s squared plus 1, dx ds is just 2s. And then y is s cubed, so dy ds is 3s squared. And since z is the natural log of x plus y, the partial of z with respect to x and the partial of y with respect to x are actually going to be equal to each other this time. And they are both 1 over x plus y. So we can see then, putting all the pieces together, that dz ds, we're going to do dx ds, which is 2s. That's not how you make it 2s over x plus y. And then dy ds, which is 3s squared over x plus y, because when we multiply the terms, we can just put the denominator. Notice we have the same denominator here. So we have 2s plus 3s squared all over x plus y. But of course, we want to get rid of the x and the y and write everything in terms of s. So we're going to replace them. And I'm going to move the terms around a little bit just to have the highest exponent first. I don't know why. It doesn't really matter. But this is my x. And that's my y. So my final answer looks like that. All right, for this last one, we've got a little bit of a challenge because we've got a lot of variables floating around. So we're looking for dw dt, but notice that w is a function of 3 variables this time. So when we draw our dependency diagram, we see that x, y, and z all depend on t, and then w depends on the 3 of those. So we're going to have 3 terms in our derivative. So we're going to get the partial of x. No, we're going to get the dx dt. X is only a function of one variable, so we don't need a partial there. Dx dt times dw, the partial of w with respect to x. Then we'll have dy dt times the partial of w with respect to y. And then lastly, dz dt times the partial of w with respect to z. Okay, so given that w equals x squared yz, we'll calculate those partials first. So the partial of w with respect to x is going to be 2x yz. The partial of w with respect to y is going to be x squared z. And the partial of w with respect to z is going to be x squared y. Then we'll look at dx dt. dx dt, since x is equal to e to the t, dx dt is e to the t. Since y is t squared plus 1, dy dt is 2t. And since z is a little crooked, z is sine of t, dz dt is cosine of t. All right, so now we just have to put it all together and maybe tidy it up a little bit. So dw dt, I'm going to take dx dt times the partial with respect to x. So dx dt is e to the t, and then dw dx is 2xyz. And then dy dt is 2t, and the partial of w with respect to y is x squared z. And then dz dt is cosine of t, and the partial of w with respect to z is x squared y. Now we're going to replace x, y, and z with what they're equal to with regard to t, so that our final answer only involves the variable t, the one variable that we're looking at here. So we'll get e to the t, and then 2x is going to be 2e to the t times t squared plus 1 times sine of t. Then we have 2t, and then we have e to the 2t. When we square e to the t, we get e to the 2t times sine of t. And then last we have cosine of t times, again, e to the 2t times y, which is t squared plus 1. Okay, so now notice that each of these terms has an e to the 2t. We see it obviously right here and here, and then if we combine this e to the t with that one, we get an e to the 2t, so we'll factor that out, e to the 2t, and then we're going to be left in our first term with 2 times t squared plus 1 times sine of t, and then we have another 2t sine of t, and then we have a t squared plus 1 times the cosine of t in our last term. And if we want, we can combine a little bit more because we have a sine of t inside of both of these. This is not really necessary, but if you want to, you can rewrite this as e to the 2t times, we'll write this as 2t squared. I'm now distributing this guy in here and adding it with this, plus 2t plus 2 times the sine of t plus t squared plus 1 times the cosine of t. Okay, so remember that as long as you're pretty good at taking a derivative, then these are straightforward problems. If you start with a dependency diagram, you're going to put the variable you are differentiating with respect to at the top, and then the variable that you're trying to find the derivative of, or the function you're trying to find the derivative of at the bottom, and figure out how many paths you need to take. Remember to multiply along the paths and then add up the terms. The number of paths should equal the number of terms in your derivative until you simplify at the end when you make any replacements that you need to